I have to confess something. I love challenges. And when you're a podcaster, what's a better challenge than dedicating an episode to visualization? Impossible, you say? Well, challenge accepted. Thankfully, I got the help of a visualization Avenger for this episode, namely Matthew Kay. Matt is an assistant professor jointly appointed in computer science and communication studies at Northwestern University, where he co-directs the Midwest Uncertainty Collective. I know, it's a pretty cool name for a lab. He works in human-computer interaction and information visualization, and especially in uncertainty visualization. He also builds tools to support uncertainty visualization in R. In particular, he's the author of the tidybayes and ggdist R packages, and he wrote the random variable interface in the posterior package. I promise you won't be uncertain about the importance of uncertainty visualization after that. This is Learning Bayesian Statistics, episode 66, recorded May 25, 2022. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the podcast, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, supporting LBS on Patreon, unlocking Bayesian merch, everything is in there. That's learnbayesstats.com. If with all that info, a Bayesian model is still resisting you, or if you find my voice especially smooth and want me to come and teach Bayesian stats in your company, then reach out at alex.andorra@pymc-labs.io or book a call with me at learnbayesstats.com. Thanks a lot, folks, and best Bayesian wishes to you all.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men dropping placebo-controlled science like I'm Richard Feynman?
Matthew Kay, welcome to Learning Bayesian Statistics.
Thanks for having me.
Yeah, you're welcome. I feel like it's a long overdue show. I've been meaning to invite you for a while, and since I'm very organized, it somehow happened only now. But I'm nonetheless very happy to finally have you on the show.
Well, I'm excited to be here. I love the podcast, so it's nice to have the opportunity to chat.
Well, thank you. And yeah, I have a lot of things I want to talk about with you. Of course, the first one will be, well, you, as usual, because I like to start with the guest's origin story, and basically how did you come to the stats and data world, and how sinuous of a path it was for you.
Yeah, so my background is in computer science. That was kind of what my undergrad was. And I was probably like 3 years into my undergrad. Well, so I did my undergrad at the University of Waterloo. The computer science department there is in the math department, which means we have to take like some stats classes like statistics and probability and stuff like that. And so I took those classes and then wasn't really using them for a couple of years, really. I ended up sort of doing a master's there as well in human-computer interaction, which is now kind of the main field that I'm in research-wise. And in that field, there's a lot of kind of empirical work that you have to do. You know, you're studying how people use computer systems. You're trying to figure out how to design them to be more effective and things like that. So, you know, we're running experiments on people, which means we have to do statistics. And so that kind of brought me back into applying a little bit of statistics knowledge, which I then had to kind of refresh myself on. I feel like it's one of those things where in undergrad in computer science, you're taking a statistics class and then you're kind of just not using it, you know, unless you're someone who goes directly into something like machine learning. And so I had to go and pick those skills back up again. That kind of brought me back to using R. And then I kind of fell in love with that programming language. And yeah, I'm trying to like I knew you were going to ask this question, so I was trying to think back to like when I actually got into Bayesian statistics specifically. And I know it was at some point during my master's, but my memory is kind of like a sieve, right? Like you asked me what I did 2 weeks ago, I'm not going to be able to tell you. And so I know that at some point I picked up Krushke's book, which I think is one of the gateways that a lot of people find, and started playing around with JAGs at some point and trying to use it to like fit models to some of the data I was doing. I think the first time I really used it for something interesting was in PhD. So after doing my master's, I went to the University of Washington and started doing a PhD there, still in kind of human-computer interaction. And I was working on this project where I was trying to do a little bit more like complex modeling of how people were responding to, what were we doing with that? We were basically putting people in scenarios and like manipulating the precision and recall of these classifiers that they were encountering, and then like trying to understand something about their preferences between like true positives and false positives and things like that in a particular scenario. And so to model that, what really helped was being able to build a model where people's choices were dependent on these different parameters. And so in order to do that, it's like an off-the-shelf model wasn't really going to be quite what we wanted. And so I kind of had to build something a little bit more complex. And I did that in JAGs. And then that, I think, was kind of the beginning of my, this is actually a really neat way of modeling things. And it's a lot more flexible than just an off-the-shelf model. I don't know I think that's enough of an answer to that question.
Yeah, you actually answered 2 questions.
Oh.
So I'd say, yeah, that's good. But basically, so you were interested in scientific topics and stats pretty fast in your studies, it sounds like.
Yeah, I think once I got into running experiments, I really wanted to, I had this frustration with the way that I was taught statistics and the way that I was doing statistics, which I think is sort of this common frustration, right? You're trying to analyze an experiment, so you learn like this tiny little decision tree around like, should I use a t-test? Should I use this model? Should I use that model? And then there's no like coherent framework that's putting it all together. And then I kind of ran into this coherent framework, which was kind of Bayesian statistical framework. And I started being able to think, all of these things are different, like special cases of this more general thing, right? Which might be, some variation of a linear model or something like that. And that kind of gave me a way of piecing everything together and then being able to think about, I have this more complex situation in this particular experiment. I can actually construct some model that represents that situation more faithfully, rather than just sort of trying to like pigeonhole it into this very small decision tree of possible ways of analyzing the data.
Yeah, there's some randomness in how you discovered Bayesian stats, but in the end, like not that sinuous of a path, right? Like you've been interested in that for quite a long time.
Yeah, I think the more sinuous thing would be my interest in uncertainty communication.
Yeah, exactly.
Because that's something that didn't really come until like halfway through my PhD. In my master's, I was doing work on redesigning user interfaces for communicating like software license agreements, which is not anywhere close to anything that I do these days. It turns out that's really hard and basically impossible, and people don't want to read software license agreements, and there's basically nothing you can do about it. That's what I learned during my master's. Then I started my PhD, and I was kind of working on this stuff where we were, what did I do? So I kind of started my PhD. I was like, well, I'm interested in human-computer interaction. There's a bunch of people at the University of Washington that do that. I don't know what I actually want to do within that space. So I started talking to different people there. I ended up working with Julie Keentz, who was my advisor through the rest of my PhD. She does kind of personal health informatics stuff. So I was doing this project where we were deploying a bunch of sensors into people's bedrooms and trying to like track different things that impact the quality of their sleep, like sound, air quality, light, stuff like that. And part of that project, we built this visualization system that people could use to see all of their data and like try to make sense of it and try to understand something about what might be causing sleep issues. And in that process, I kind of realized, one, there's a lot of uncertainty in that data. There's noise in the sensors, and the sleep tracking, some of the sleep tracking equipment is not actually that reliable when it's trying to classify things like wake up events and stuff like that. And then there's also just the complexity for a sort of layperson looking at their data, trying to make sense of it. And that kind of got me interested in this problem of how do we communicate relationships between data where there's uncertainty. How does someone sit there and try to understand whether or not light or sound or whatever might be related in some way to negative sleep quality? And that kind of got me a little bit interested in this problem. And then I ended up doing an internship at Microsoft Research where we were looking at weight tracking and how people understand fluctuations in their own weight when they step on a scale, which also has all of this uncertainty associated with it. And then from there, kind of the latter half of my PhD turned into this like uncertainty visualization work where I was trying to understand how to communicate error and probability to people in ways that they can better understand.
I see. So, like, stop anticipating all my questions, Matt. Impressive. Yeah, okay. And so, of course, naturally, when you started focusing on how do we communicate uncertainty, it was tied to Bayesian stats.
Yeah, and I think that, I mean, it's interesting, right? So for a while, I think I really sort of drank the Kool-Aid around, oh, like, if you're going to try to communicate uncertainty, like, probability is the only way to do it. And this is the only sort of reasonable framework in which to think about uncertainty. I don't really think that way anymore, which is maybe a little bit of a weird thing to say on a Bayesian stats podcast. But like, I think it's interesting, right? I think some people make this argument for Bayesian statistics where the idea is, well, you want to be able to quantify the uncertainty and say like the parameter in a model. But if you use a frequentist approach, you can't. And I have to preface this, like I'm saying what I think some other people believe. If you use a frequentist approach, you can't quantify that uncertainty in a reasonable way. And I think that the reality is a little bit more complicated. I think part of the purpose of statistics is to put into someone's head some reasonable subjective uncertainty about some fact in the world, right? Which might be, you know, what I think a mean is, or what I think this parameter is in a model. And whether you fit a frequentist model or a Bayesian model, people are still going to end up with some kind of subjective uncertainty, possibly in a sort of like vaguely distributional way in their head around what they think a parameter in the model is. And so it's not clear to me that like, and the relationship between that subjective uncertainty and even say like a probability from a Bayesian model is not going to be normative in some like statistical sense, right? We don't perceive probabilities and act on probabilities in a way that is normative, right? Like in the sense that if you gave people a bunch of incentives and then like figured out using Bayesian decision theory what they should do, and then gave them the probabilities that they should presumably be able to use along with those incentives to come to that decision, they're probably not going to come to that decision, right? So like the way that we perceive and use probabilities is not particularly normative. And so then to say, well, oh, you know, if we want to understand the uncertainty of this thing in a model, we should definitely use Bayesian statistics because it gives you those probabilities. It's like, oh, that's fine, but they still end up being interpreted by a human in a weird way. So what do you do with that information? So I think what I'm trying to say basically is the argument that because Bayesian models allow you to get probabilities around parameters is not as compelling to me as it used to be. I think what's more interesting about Bayesian modeling is the flexibility it gives you to create models that you otherwise wouldn't be able to, or the flexibility to incorporate prior knowledge. Those things to me are what's really powerful about it, less so the sort of, oh, I really want probabilities parameters argument. Because you can even still do that. You can construct these things called confidence distributions, which don't give you probabilities in a normative sense, but give you some kind of distributional representation of uncertainty in a parameter in a frequentist model. So I guess this is my kind of like, I used to think it one way, and now I think a little bit of a more nuanced way. And I think the advantages of Bayesian models are a little bit less the, oh, probabilities are wonderful argument.
I see. I'm always in favor of people trying to have two contradictory ideas at the same time in their mind and thinking that both could be true or both could be false, which our brain hates doing.
Yes.
So definitely I encourage that kind of nuanced thinking. What I'm thinking about, though, is that the interpretation, though, is not the same, right?
Right.
Because like the interpretation of a confidence interval in the frequentist stats, you still cannot interpret it as the way we want to interpret it naturally, right?
Right. And so I totally agree with that. I think the way that I think about it a little bit, though, is even though that is technically true, people are going to do it anyway, right?
Yeah.
I kind of take this like empirical kind of like, I think this kind of comes from my human computer interaction kind of background, right? Which is sort of, we always talk about like not blaming the user, right? So you want to build tools in a way where people use them as normatively as possible, right? Or as well as possible for the goals that they have. And if they're not using them particularly well, you don't blame the user, you blame the tool in some sense. And so from that perspective, I think there can be an argument to, well, you should give people models that express uncertainty in a way that they will then use correctly, hopefully. And from the perspective of, say, like credible intervals versus confidence intervals, well, you give people a confidence interval, they're probably going to, well, the thing is, so what I used to think is, if you give people a confidence interval, they're going to interpret it as a credible interval, right? And I think a lot of people make this argument. I think the reality is, when you give people a confidence interval or a credible interval, they interpret neither of them as either a confidence interval or a credible interval. They interpret them as something else entirely.
Yeah. So that was something I was which is like, but then it comes from the fact that our brain is bad at interpreting probabilities, right? But like can you even say the real probability? Because like David Spiegelhalter, for instance, would say, no, there are no real probabilities. But if you want, like the mathematical probability is really the Bayesian credible interval. And that's what we should get back from the tools, ideally.
Sure.
But even if we do get that back, we, Homo sapiens, are not going to interpret that exactly as we should interpret it. But that does get us closer to better interpretation.
Right. So I think that that's reasonable. I mean, part of this to me gets to differences between probabilistic and possibilistic notions of uncertainty. So there's the like multiverse analysis idea, or like specification curve analysis idea, or like sensitivity analysis, comes under a lot of names, right? So like multiverse analysis was kind of Andrew Gelman's take on it, right? You know, you have a bunch of different ways you can analyze a data set. So you do all of the combinations of those, and then you get, say, not a single credible interval, but like a set of credible intervals, right? And then you have to start talking about like possibilistic uncertainty, right? There's probabilistic uncertainty where you have weights associated with different outcomes. And then possibilistic uncertainty is sort of, well, you have a set of possible outcomes, but you don't have any notion of one being more probable than the other, or really any way of saying that, right? So you have a set of credible intervals, and basically all you can do is say, well, one of these might be a reasonable credible interval, right? And then the question is like, well, how do you make decisions in that context, right? How do you, as a human being, I couldn't expect you to understand a single credible interval, and now I'm giving you a set of them. Like, how do you make decisions here, right? I think it's a really interesting question. Like, we want to be able to do more robust data analysis. We want to be able to more accurately reflect our uncertainty and think about it and reason about it. But we also have our own limitations in doing that.
Yeah, for sure. And my way of thinking about that is that, like, it's at least in the Bayesian framework, you get something closer to something that's really useful. And also on top of that, you have the flexibility of the models that you talked about, and that maybe I'd like to talk about more after that. That being said, I do think that probably there is more work to do in uncertainty communication in the frequentist world than in the Bayesian world, precisely because like uncertainty is extremely hard to interpret and understand in the frequentist framework. And also it's something that people are less aware of probably, because there is less of an emphasis on that. Whereas in the Bayesian world, you see a lot of people like being in that framework exactly because they needed probability estimation and things like that. So yeah, you've got a lot of work, it seems.
Yeah. You know, thinking about this, I think there's also an ease to it, right? So one of the things I like about the Bayesian framework is you fit especially if you're using like some Monte Carlo method, right? So you're using like Stan or JAGS or whatever, and then you get this joint posterior as a bunch of samples from the joint posterior. Your uncertainty communication problem is now a lot simpler, right? You're basically just trying to take that joint posterior as a bunch of samples and then take slices through different margins of that distribution and then try to communicate it in some way, right? I think the thing that is difficult about the frequentist framework is getting that uncertainty for a particular slice through that equivalent of the joint posterior is more of a pain in the ass, right? Like that's basically what it is. Just like technically speaking, I can sit there once I have the samples. It's really easy for me, as long as I have tools that are good at manipulating those samples, to get the distributions that I care about, that I want to communicate or make decisions from.
Interesting. Can you just quickly talk about the fact that you said that the models you can make in the Bayesian framework are more flexible and so on? So can you just elaborate a bit on that?
Yeah, sure. I guess I can give you a recent example. So one of the projects I'm working on right now with some of my students and one of my postdocs is we're basically trying to build this model of biases in people's perceptions of a probabilistic forecast. So it's an election forecasting thing. So say you have like a two-party election system and you have a distribution for the vote for one of those two parties, right? Because if you have a two-party system, you only really need the one distribution, right? It's, if one party wins, the other one loses. Or say we're talking about a single seat, right? Like for a governor or a presidential election or something. So if I'm trying to communicate this to someone, I can show you, say, like a predictive distribution for what the proportion of vote will be for candidate A versus candidate B, for example, right? So we're basically running this experiment where people are taking bets on, or choosing to take bets on, the likely outcome of some election. And so this is a pretty simple two-alternative forced choice model, was what a psychologist would call it. It's basically they're trying to choose whether to take a bet for a candidate or take an alternative bet for something simple like flipping a coin or something like that. But we can give people a bunch of different versions of these forecasts with a bunch of different potential probabilities. And then essentially what we want to do is model the relationship between the probabilities we're showing people, the probabilities we think that they're perceiving, which is some latent thing that we can't actually measure, and then the choices that they make in this betting task. And so in order to set up this model, we can take some models of probability perception from the literature and basically like embed this as a submodel inside this sort of bigger model of betting decisions in order to estimate this kind of latent parameter, actually two parameters that describe the biases in their perceptions of probabilities. I would not want to try to estimate this model using a frequentist approach because without the priors that we set on it, it would probably not converge, right? And like, this is where I think a lot of the flexibility comes from, right? Like, yeah, you could try to like use maximum likelihood or something to fit this model, but it probably it wouldn't converge. It would just die, right? In order to set up a model even like this, which is not that complex, but it has like this weird little submodel and a couple of latent parameters. And it's also a hierarchical model over all of the people that were running through this experiment. I have no confidence that I'd be able to fit that model without being able to put some priors on these parameters.
I see. So basically, if I try to summarize for you, the flexibility comes from, one, the way you can structure the models and feed the data generating process, and two, the regularizing effect of the priors.
Yeah. And I think also part of this, is also part of the draw of the sort of Bayesian framework is the languages that we can use to do this, right? The fact that I don't have to wander around through the R package universe to try to find someone who's like figured out a good way to write, an estimator for this weird model, right? I can just be like, all right, I'm going to try to write this thing in Stan, or I'm going to try to write it in BRMS. And they have these nice flexible syntaxes where you can compose different pieces together to create this model that is accurately, to our understanding, representing the phenomenon we're trying to study without having to like go and learn some new syntax for some other weird new package, right? I think a lot of this comes down to like the expressive power of these languages. They're constructed in such a way that the authors of those languages have not sort of thought of every possible model you could fit there. They've constructed something that is so expressive that people can come along and create the models that they need for the phenomena they're trying to study.
Yeah. So in a sense, you can stand on the shoulders of giants.
Yeah.
Yeah. I mean, we're going to talk a bit more about API building and so on. But yeah, I can see that it's something that you're really sensitive to. So that's cool.
Yeah.
Okay. Yeah. That's clear in my mind now. So thanks a lot for that. And actually, if we focus a bit more on uncertainty visualization, right now, the work that you're doing, do you focus more on some sorts of models, on some framework, Bayesian or frequentist, or like is your research on uncertainty visualization and communication pretty broad?
That's an interesting question. So are you asking, like, in the context of uncertainty visualization, am I more interested in communicating Bayesian, like, uncertainty in a Bayesian framework versus some other framework? Or that's kind of the question?
Yeah, because I guess that the ways to do so quite different, because the results of the model, like what you get back from the models, is different, although the underlying goal is the same. But I'm just wondering about basically the topics you are particularly interested in when you're like right now, basically in your research.
Yeah. So for a little while, I was doing a lot of more communicating probabilistic uncertainty, which I still do, right? And so from that perspective, I think it really is steeped in kind of the Bayesian framework. I have a predictive distribution for some event that I think someone cares about, right? And I want to try to communicate that to them in some way that they understand. Say, like the outcome of an election, like I was talking about before, right? And I have ongoing work right now where we are still doing that kind of thing, right? We're trying to understand how people understand, say, a probabilistic forecast like an election forecast, and how we can redesign those forecasts so that people will better understand them, make better decisions from those forecasts, better understand, say, why a forecast could be wrong in a sort of simplistic sense, right? Where, say, the forecast says candidate A is most likely to win and candidate B wins. How do people judge that outcome, right? If it said candidate B had a 30% chance of winning and then they won, right? Do people think that that's a bad forecast? Do they think that, especially in the election context, I think it's important, do they think that that means the election was rigged or something like that, right? Like, I think these are actually can have very important societal consequences, the way that people reason about unexpected events, right? And really, I mean, like, yeah, the probabilistic forecast says 30% chance. That's not low. That can definitely happen, and it does happen.
Yeah, but for a lot of people, 30% is low.
Right. And this gets back to these like probability perception models and people sort of rounding low probabilities down or rounding high probabilities up and things like that, right? And so this was the thing I was alluding to earlier, right? The basic idea behind that project is, or one of the ideas behind that project that we're going to try is, if we can estimate this probability perception curve, you can basically just take a probability distribution and stuff it back through that curve and show people a different probability distribution that you would expect them to perceive as the one that you're trying to communicate, right? And so in this like 30% example, that might do something like bump that up to like 40% or something like that, to just try to make it sort of seem a little bit closer in the subjective sense and try to make that subjective sense match what we're actually trying to communicate.
Yeah, I see. Yeah, in a sense, you could have like kind of like a logistic curve, right? Where it's like, it seems like our perception of probabilities like that, like,
yeah,
where you would have on the x-axis, you would have like the mathematical probability, which would be real probability. On the y-axis, you would have Homo sapiens probability. And like actually a 0% chance in Homo sapiens mind is equal to a 30% chance. And then you go to the linear part of the curve, and then like it's normal, like we follow the real mathematical. And then when we go back to high probabilities, like for us, 80% chance is like 100% chance.
Yeah. And that's actually exactly so. There's this model called the linear and log odds model of probability perception. And basically that's the idea, right? If you take the logit of both the true and the perceived probabilities, there's often a linear relationship. And this kind of holds across a bunch of different studies over like many decades of probability perception. And yeah, so the idea, once you have that relationship, you can take a probability distribution and just transform it and show people a different probability distribution. And hopefully, so we're kind of in the middle of this right now. We're trying to see if we can actually use that to show people different distributions that they will hopefully perceive a little bit more normatively. I mean, this itself is kind of a controversial idea, I would say, in visualization. This idea of, some people call it debiasing. I'm not a big fan of that term, but like, so the classic example of this is like where we have biases in our area perception, right? Like if I show you two circles and ask you the ratio of their areas, you'll tend to overestimate that ratio. And so one of the things people will do sometimes in visualization is they'll say, well, you know, this relationship, our perception of areas follows this power law. We can estimate the coefficient of that power law, and then we could modify the areas of objects in a visualization such that you would hopefully perceive their ratios more correctly. And some people say, well, yeah, like this is a very reasonable thing to do to sort of like debias these areas. Some people say, well, now you're lying to people, right? Because if someone like took out a ruler and measured the diameter of all of those circles and then like calculated their areas and then took the ratio of those areas, which obviously no one would ever do, those numbers would be wrong, right? And this is kind of the same thing. Like if I show you this like transformed probability distribution that I should expect you to perceive correctly, but if you actually sat there and like calculated the areas of, say, the density or something like that under the density curve, like, yeah, you would get the wrong answer.
Yeah, for sure.
So it's complicated. I think there's no easy solutions here, but I think it's worth trying to think about how we can try to help people better understand uncertainty through some of these techniques.
Yeah, I mean, that's complicated. That's super interesting. I like that because it's also related to like kind of epistemology at the same time, and also psychology, how people perceive the world. And like it's really like diverse and broad. It sounds super interesting.
Yeah. And it's fun, right? Like, you know, it's fun to kind of work across these areas and try to think about these sort of weird problems that do, as you say, like they kind of come down to epistemology. Like,
yeah,
how do we actually form knowledge about the world and understand the world?
Yeah, exactly. Actually, do you, based on what we talked about, do you have some current best practices that you saw and try also to implement in your own work? Best practices to visualize and think about uncertainty in the Bayesian framework?
Yeah. Do I have best practices? Yeah, that's a good question. I mean, I think it's interesting. So I've done this work on this thing called frequency framing, or like discrete outcome uncertainty visualizations. And this is kind of the idea that rather than showing, say, like a density plot or something like that, some continuous encoding, we'd call that a continuous encoding, like kind of in the visualization parlance, right? Because you have a continuous variable that's being mapped onto some, what we would call a visual channel, which is just like little jargon for like kind of like geometric variables and visual variables that you can manipulate, that people can see and like decode into data, right? So a density plot is just a mapping of the density function onto a positional visual channel, right? As in the y-axis is a positional channel. So you've mapped that function onto the y position. Other channels are things like color or size or things like that, right? So density plots are this continuous encoding of uncertainty. I've done a little bit of work on these things called quantile dot plots, where you take like some number of quantiles of the distribution, you know, like 20 or 50 or 100 or something like that, and then you make a dot plot out of them. Here, dot plot is a little ambiguous because it actually has two definitions, but the one that I'm referring to is more like the kind of like bee swarm kind of thing, or, you know, where the like histogram sort of dot plot, where you take all of, say, the points in a univariate distribution or all of these quantiles, and then you stack them up and it makes sort of like a histogram, but it has a bunch of dots. So these things are kind of useful because they have some nice perceptual properties. Like I was saying before, actually, this kind of connects. We have this bias in our area perception, right? And so density plots are actually kind of potentially problematic, because one of the interesting things about density plots, I think, is there's this common misperception that the height is probability, right? Like, I feel like you run into this all the time. Like, people think that the height of the density curve is a probability. It's not. Like, the thing that you need to do with a density plot mostly is look at areas, right? And so that connects back because, well, our area perception is biased. So maybe a density plot is not such a great idea in some circumstances. The dot plot is nice because if you're trying to look at essentially the equivalent of areas, you're looking at the number of dots out of 100, say, that are within a given region. And that allows you a potentially more intuitive way to do basically these integrals, right? And so that's like one technique that I've used. And I think it's useful in kind of like lay communication. And that's mostly where I've studied it. So it's interesting because I've studied that, but then when I write papers and like fit models, I'm usually showing like density plots or CDFs and stuff like that. Right. And so it's like, oh, like I've studied this uncertainty communication technique and I think that it's useful for lay audiences. And then I go and write papers about it and I use density plots.
But is it because the audience who reads the paper is actually more used to the density plots? Or is it because it's your own doing here?
It's a good question, right? I think there's a couple of things. So one of them is that, I mean, visualization is very complicated, which is kind of a tautology, maybe, to say that. But yes, visualization is very complicated. One of the reasons why it's complicated is people bring their past experience and context of basically, some people will call them schemas or like templates, basically like chart types, right? I've seen this visual pattern before. I associate it with this, right? And I think one of the issues with dot plots, for example, especially in a scientific context, is if a scientist comes and sees a dot plot, they probably think they're showing raw data, right? And if I'm using a dot plot to communicate uncertainty in a parameter, I don't want people to confuse that for some visualization of raw data from that I used to fit the model or something like that. And so this even comes up with things like even densities, right? Because people will use like violin plots, for example, a lot for descriptive statistics visualization to show raw data. If you then use a violin plot to show a parameter in a model, there's a potential confusion for readers who aren't as familiar with, say, Bayesian modeling to think that you're actually showing them a visualization of raw data. And I've encountered this before, and it's difficult, right? So one of the things that I do to try to mitigate against that is I don't use violin plots as much anymore, but even like density plots, because I still think you can have this confusion, you can make them look different than the density plots that people typically use for raw data, right? If you overlay intervals and draw those intervals in a particular visual style that looks different from a box plot, people will hopefully realize that you are showing them a visualization of something different than what they've seen before, and then try to like understand what that is. But if you just showed people, say, like a box plot for a parameter, or a box plot with two mirrored densities behind it, the way people usually draw violin plots, my guess is like some number of people will misinterpret that as a visualization of raw data. So it's like, even if you have the right encoding that you think is good for a problem, you still have to think about what is the history of your audience with this kind of encoding and the like visual style of it that will cause them to potentially misinterpret it as something else.
I see. That's always hard. And also, like, I guess there is always the decision to make between how much do you want to help people realize that the reasoning is biased, or make the tool biased in the way that humans are so that it matches the way humans think. It's like, what do you do? Do you try to correct the way we think because actually we think in a distorted way and the reality is not like that? Or do you actually distort the tool that reflects the reality more, but then you present the results to humans? You know, it's a bit like when you see a picture of a black hole or you hear a black hole. Well, you don't, right? You don't see a black hole and you don't hear a black hole, right? It's like it's transformed. The data are transformed so that we can see and hear them.
Yeah.
And that's necessarily an approximation. So yeah, I guess you always have that tension, right? Where do you want to make people believe that they are right, or do you want to help them understand that there is distortions in the way we think?
And I think that in the scientific communication context, in like a scientific article, right? I think that there's probably some kind of value related to transparency or something like that, which suggests that this kind of distortion, if you want to think about it as a distortion or debiasing or whatever, is probably not appropriate in that context, right? But yeah, I mean, it's hard though, because there are ways in which it's uncontroversial. So the uncontroversial version of this is anytime you look at a color scale, right? If you want a color scale that is perceived as uniform, it is mathematically not linear, right? And so like that's the uncontroversial version of that.
Yeah. And it's like the Spotify random algorithm, you know? Like I love that story where like Spotify, when they started having the shuffling, it was purely random, but then people didn't believe it was random because sometimes a song would play twice.
Right, yeah.
And it's like, and for us, that's not random because random must be like perfectly, like uniformly random, if you want. Whereas real randomness doesn't work like that, right? You can't see patterns in randomness. And that's like our brain hates that. We see pattern. No, there is something. There is a conspiracy going on. And so actually Spotify changed the algorithm so that you could not repeat the song too much. It's like, it's amazing. I love that.
Yeah.
Okay. So I see what you mean. And it's always, I guess it's always something that you to make a decision on. And maybe the easiest case is when there is a true mathematical definition in a way, like a black hole has a mathematical definition equation. And so in that way, you know that normally it's that, but then you distort it because we have not the ability to perceive it as it really is. So you have to, in a way, put it through the logistic function so that we can perceive it.
Yeah.
Then the question is like for probabilities, for instance, if you don't believe that true probabilities exist, they exist mathematically, but do they really exist? Well, actually, it may be easier because then you can just say, well, no, the way that humans perceive probability is just as right because, well, probability doesn't really exist.
Yeah. Then you would run into the problem of what is the appropriate transformation to these probabilities. And I think there the problem is, well, it is context dependent, right? And so from that perspective, I think there is sort of an argument that the most neutral way of presenting it is as the raw probabilities. And then if someone wants to think about how they should transform that to make a decision appropriate to themselves, they can apply that transformation somehow.
Yeah. And actually, how does that translate to what you have learned about developing APIs and like good APIs that work well for a particular problem, but that are still flexible in a way?
Yeah. I mean, this gets back to the earlier bit of our conversation about why I think some people are drawn to Bayesian modeling. And I think it's, in some sense, it's actually the languages or the APIs that we use, right? So for me, I think about this a lot in the visualization space, right? Because I spend time writing software and APIs for uncertainty visualization, things like ggdist now, and what was originally tidybayes kind of started during my PhD, actually, when I was starting to build these models and then like trying to figure out how to visualize their output and realizing that it was kind of a pain. And so I built tidybayes originally as a way of just munging the output of these models into a form that it was possible to use with ggplot. And ggplot has this very particular style of API where you really want kind of like long format data frames, right? So every row in the data frame is a draw from the posterior, right? And getting output of these models into that format is kind of a pain. So I built like a little API for doing that. That was tidybayes. And then that included some visualization components that eventually sort of grew, in some sense, to be even the bigger part of that package, which I then split off into ggdist. And so one of the very first things that I realized all of this process was the really early version of tidybayes had a function called, I think I called it like GGI or something like that. It was for creating eye plots, which are basically like violin plots, right? So it's like a mirrored density around a point estimate and like maybe one or two intervals that you want to try to use to communicate the uncertainty in a parameter. And originally I had a function called GGI, which you would pass in, say, a data frame, and it would construct the entire plot, right? So it would create the ggplot object and then all of the layers that were associated, that were needed to create this like I thing. And as I was creating that function, I eventually realized that I was just like adding parameters and parameters on top of it, and eventually reaching the point where I'd essentially have to recreate ggplot's entire like syntax, because it was outputting a ggplot object. It wasn't outputting a single layer that you could add to a ggplot object, which means if you want to do something like faceting, well, you basically have to have another parameter in that function to do faceting, even though ggplot itself can do faceting. Like it has a thing you can add on to it to make faceted small multiple plots, right? You know, you say, I want to facet by this other variable, and then it gives you a bunch of little plots that are different, the slices through the data conditional on different values of that variable. And so I kind of realized that like there's what you really want to do with an API is I think about it more as language design, right? You want to construct these atomic components that are composable in a way that is useful, that allows people to construct something that you didn't think about in some principled way, right? This is, I think, one of the reasons why ggplot is so popular, is because it has this property, right? You specify aesthetic mappings, which are mappings of variables onto things like color or size or position, right? Or X or Y or whatever. And then you supply geometries like points or areas, or even like statistical transformations combined with geometries. So like a density transformation combined with an area geometry is a density plot, right? There are these components that you can compose and recompose to create what you want as a visualization. And the way that you compose it has these rules that you can learn that allow you to create things that Hadley Wickham, the creator of ggplot, would have never imagined, right? And that to me is like the sign of a good API. I think like this is the same thing as I was saying before with something like Stan, right? They don't think of every model you could create with Stan. They think of the atoms and the rules for composing them that allow you to create those models. And to me, with visualization APIs, like if I'm extending ggplot to do something else, I don't want to create the function that gives you the ggplot. I want an object, right? I want to create the function that gives you a layer that you can compose with other layers in a ggplot object. And so that's where ggdist kind of evolved to. It's essentially a package with like 3 geometries in it, this like slab interval geometry, the dots interval geometry, and the line ribbon geometry. And they're basically just like 3 different classes of ways of visualizing uncertainty. And within them, you can reconfigure them. So like the slab interval geometry, you can reconfigure to give like density plots, like, you know, gradient plots, CDF plots, a whole bunch of other things, and a bunch of things I've never thought of, right? Like people do weird stuff with it that I've never thought to do. People started making rain cloud plots with them, which are basically a composition of a density plot on top and like a dot plot underneath, right? And so you see like the density, and then it kind of looks like a cloud with like data raining down or something.
Right, yeah.
Yeah, they're kind of cool, right? And or like I put a bunch of work into making it so that you can map variables across the slab. So basically the way that it works is under the hood, it's generating values for the density function and the CDF simultaneously, and it allows you to map those onto visual variables. So you can do things like there was a paper a while ago on this weird kind of uncertainty visualization where it would show you a density plot, but then outside of, say, like a 95% interval, it would kind of fade the tails off, right? So the center would be filled in, and then the tails would kind of fade off as a way of trying to like somehow intuitively like emphasize the uncertainty or something. This is really easy to do in ggdist, and I didn't even like intend that you could make this plot, because if you have the CDF, you can determine the bounds of the interval, and then you can just write a tiny little expression that makes it so that if you're outside of the interval, you map the CDF onto the opacity, and then that just causes it to fade out, right? Or you can map the density onto the opacity. You either have to take flip the CDF so that it is sort of symmetric, or you can take the density and fade it. But it's just like a tiny little expression you can stick into the specification, and then it creates this effect, right?
Yeah, it's basically like important building blocks that then you develop based on it. Yeah, that's cool.
Yeah.
What I wanted to say is, so you have these building blocks that then allow people to make what they want on top of it without being too... So that way you can be general and specific at the same time.
Yeah, but there's of course a balance, right? So like the problem with going too general is then people don't know how to use your API.
Yeah.
Right? So ggdist has a bunch of like shortcut geometries in it, which are just combinations that I think are useful, right? To make like, say like the I-plots I was talking about earlier, right? Because you don't want to have to memorize like all of the different ways of combining these things. But yeah, like that to me is like the goal. You're always like, and the thing about ggdist is I've rewritten it so many times because you kind of like expand the space of what's possible. And then you step back and you kind of reflect on the relationship between everything that you've created and try to come up with a more general way of expressing the same thing that you've already written. Right? You're constantly like trying to come up with a formal description, or at least the way that I think about it is you're trying to like formalize the objects in this space in a way that the relationships between them are useful. And then you kind of get to a point where you're like, well, now I have to rethink that entire thing. And then I kind of rewrite it.
Yeah, completely. Time is flying by. And I want to ask you at least two other questions before closing up. And actually, it's like a bit more generally, what do you think right now are the biggest hurdles in the Bayesian workflow? I mean, especially from your point of view.
So I think there's two things that I think are kind of hard. One of them is prior setting. I think prior setting is incredibly difficult. And especially prior setting where you have some complicated joint structure, I don't know, like a covariance matrix or something like that. Or you have nonlinear transformations in the model, right? Just because we're so bad at reasoning about them. The simplest model that it's hard to set priors on would be just like a logistic regression, right? Because our reasoning about what those priors mean in that space, I think, is just often so incorrect. And the more we can get tools where you can just even just like interactively set priors while it's doing like, I don't know, like prior predictive simulation or something, so you can see what it is you're actually doing. Like if I could sit there with a Stan model or a BRMS model and like tweak priors and have visualizations of the prior predictive, like just churning as I'm doing that, that would be incredibly useful, right? And so I think that's a big problem.
Yeah, for sure. I mean, I can see that way. Each time I teach a workshop with PyMC Labs, setting priors is incredibly complicated, both conceptually, mainly conceptually, right? And we have a whole lesson is dedicated to how do you choose your priors. And then when we teach about generalizing in our models, I hammer that point home. Link function, hard to set priors.
Yeah.
And we do have now the pm.find constraint priors function in PyMC, which I worked on and with a bunch of other guys at labs. That was super interesting to work on, way more complicated than what I expected.
Yeah, I think I remember seeing that on Twitter, yeah.
Yeah, well, even that, there is still a lot of things to do. And yeah, as you're saying, it's like hard for people to reason about. Also, it's because really beginners or people coming from the frequency stats world have a lot of anxiety about choosing priors. And it's like, what's the best prior? There is no best prior. What? How is that possible? And it's just like, paradox of choice, basically. Because if there was a best prior, then probably we could optimize for it and we could just tell people, just use that function that will automate the choice of prior for you. But it's not like that. And so that's what makes it super complicated in part.
Yeah. And I think then like trying to figure out setting priors on multiple parameters and like how those priors on those, say, two parameters interact with each other to sometimes completely like screw you over, right? Like, or do something you didn't expect at all, right?
Yeah, exactly. And then also when you have to check when you compare forest plots, but you have to be careful if you want to compare two variables. You can look at the forest plot and see whether the uncertainties interact or not, like overlapped or not, but you should compute the difference between the two because the two parameters can be correlated. And so actually just looking at the forest plot and the uncertainties individually cannot tell you about the uncertainty of the difference. And that also is related to the priors. And yeah, so definitely there's something really hard. But the good thing is a lot of people are working on that, right? On the PyMC side, like we've developed that thing. And I know it's something that we always try to improve for his clients on the lab side. There are also a lot of people doing a lot of cool stuff on the really pure open source thing with PyMC. You work on that. I know Aki Vetari and all the team at Alto and Paul Björkner, they work a lot on that, and it's like super promising. And by the way, people, listeners, if you're interested in that, you can listen back to Aki's episode on here and Paul. So Paul, I'm pretty sure it's episode 34. Aki, I'm not sure. I would say 39, but I'll put that in the show notes. Yeah, okay. So I have not enough time. So I'm just going to ask you one last question, but you can choose it. So either you tell me what you are doing right now to work on these prior setting stuff, or you can tell me more generally, what the future of Bayesian stats in your field look like to you.
I don't know. I don't have a strong preference.
Okay. Then tell me maybe more about the future. Tell me about the future.
The future. Okay. Yeah. So what does the future of Bayesian stats look like in my field? I think it's promising. I see a lot more people using it in papers these days. I think that, I guess a bit more about my field. So kind of broadly human-computer interaction, but a lot of these days is kind of information visualization. And I see a lot of people starting to use these kind of models, especially in the information visualization space. And I think especially in the uncertainty visualization kind of subfield, I think it makes a lot of sense, right? People who are already thinking about uncertainty communication are more predisposed to think about the use of Bayesian modeling, right? And I think that's kind of the in. But then there's also a lot of people who are talking about, are there better ways of analyzing our data? Are there better ways of communicating our data? I think that's like one thing that's really nice about the visualization field that is different from some of the challenges I see in other fields, right? So I think when I talk to like psychologists who are using Bayesian statistics, they have this, I think they face this struggle, which is sometimes that they're worried that reviewers are going to push back against it, or if the reviewers see an unfamiliar visualization, say of like posteriors or something like that, they're going to be kind of afraid or like push back or something. And in visualization, we're a little bit lucky because we don't have that problem, right? If you make an interesting visualization that's effective, that someone hasn't seen before, that a reviewer hasn't seen before in a paper in the visualization field, they're going to be like, oh, this is interesting, right? because we study visualization. So we're kind of interested in new visualizations, even if they aren't the subject of the paper, they're just a thing that's being used to communicate the results. So those challenges, I think we don't face. It's more convincing people that it might be interesting to try these approaches. And more people, I think, are.
Cool. Well, thanks for that. That's indeed encouraging. So before letting you go, though, I have to ask you the last two questions. I ask every guest at the end of the show. So if you had unlimited time and resources, which problem would you try to solve?
Yeah, this is a funny question to me. So if I had unlimited time and resources, I would probably, for me, like keep doing the things that I'm doing because I enjoy those problems and I think that I'm reasonably good at them. But the unlimited time and resources thing puts a bit of a spin on it. There are a lot of problems in the world I would like to have solved that I'm not the person to try to solve them, right? I think there are a lot of social issues, I mean, especially in the US right now, but all over the world, there are things like climate change, all of these things that I personally consider important, but I also know that I don't have the expertise to solve. So probably if I had unlimited time and resources, I would keep working on the things that I'm working on, but then like pay someone else to solve all of those problems. Someone who actually knows how to solve those problems.
Good one. I love that. First time someone actually uses the resources viable of the equation and not the time.
Right.
Love it.
I'm fine with the time I would probably honestly go off and like start a research institute so that I could literally just work on the things the research problems I care about, but then pay someone else to try to solve climate change or something.
Awesome. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah. So I think when I thought about this question, I was like, what would be an entertaining dinner? And my conclusion to that was essentially I think it would be entertaining to have dinner with Doc Brown from Back to the Future. I don't know if he's a great scientific mind, but he's kind of insane. And I think it would probably be weird and interesting to talk to him.
Well, perfect. Love that answer too. I definitely want to be at that dinner.
Yeah.
So you have my email now. So please tell me when that happens.
Right.
Okay, well, thanks a lot, Matt. That was really, really awesome to talk to you. I learned a lot. I have to say, uncertainty visualization is way broader as a topic than I had imagined. And so I went a lot off script in that episode. Listeners don't know that, but that's cool. I love when that happens because that means there are a lot of things I learned. And so I hope it was the same for listeners. So as usual, I put resources and a link to your website in the show notes for those who want to dig deeper. So yeah, there is show notes about everything, a lot of things we talked about right now. So papers to visualizations you talked about. I'll also put a link to the pm.find constraint prior function. Hopefully it's in the docs already. But yeah, things like that, because we talked a lot about graphs and plots. Of course, in a podcast, it's hard. So definitely, if you're interested in these things, go to the show notes, guys. Matt and I will add things over there. And on that note, thanks a lot, Matt, for taking the time and being on this show.
Thanks for having me. Yeah, it was a lot of fun.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.